So we'll talk about the free body problem and a flux-based statistical prediction of it. This problem has a venerable, long history. It's a very rich physics problem. So we'll start with describing the problem and describing its history, which generated very good physics along the ages, along time. And then we'll go on to discuss the results of this paper and comparison with numerical simulation, and very little of the derivation, but mainly I will be content with describing the results. And I will end with a discussion. Please feel free to stop me at any point if I'm skipping steps or anything. And this will be based on work that was posted to the archive already. And there is also some ongoing continuation work with members of my group, Lior Lederer and Shubhajit Mazumdar. So let's go on to describe the problem. What's the next key here? Okay. So we're just discussing the three-body problem in Newtonian gravity. So we have three masses, M1, M2, M3, with some initial positions and velocities, and the force between them is just the Newtonian gravity. And the goal is to predict the long-term motion, okay? So the problem is extremely simple to formulate, but as we'll see, it's extremely rich and not so easy to get around. And now I want to show you a video, so I will...
The slides are not moving forward.
Just a minute.
We're still stuck with the first slide. Okay, now...
It didn't move forward for you?
Now we see something that says video.
Okay, so I'm going now to change the... I'm going to try and change it to show the video. Just one moment, please. The menu disappeared on me, the menu of the share screen. Where is it? Maybe I should first unshare the previous screen. That's the thing, I think. Just one moment. Oh, here. Okay. Good. And now. Okay, Avishai, can you see the screen now of a video? YouTube, yes? Okay, so I want to show you a computer simulation of the motion of the system so you get the feeling how it behaves. We'll see here three colors corresponding to the three bodies. These are comparable masses, but not exactly equal. We'll have here blue, yellow, and green. Blue will be lightest. Let's call it 12.5 solar masses. Then yellow will be 15, and then green will be 17.5. So between 12.5 and 15.5, comparable but not equal. Let's see how the system behaves. We're going to start with two bodies and the third one being thrown at them. Okay. Is it visible?
Yes.
Great. So you see it's extremely random motion. Each time two of them come very closely in a close encounter. Here one of them gets thrown out, but then it returned. And we have a year counter at the top. This goes on for a while, for a rather long while, in fact, in this specific case. So you see, until one of them gets thrown out, but it doesn't go over the escape velocity in this case. Another one gets thrown out. Shall we get an escape or not? So okay, it's returning again. The center of mass, we're in the center of mass frame, so it always returns to the center. Here again, the yellow guy gets thrown out, but not strong enough. And eventually, one of these so-called ejections will be strong enough to cause an escape, where the system disintegrates and will never recombine again. Okay, not yet. Again, it goes into a very random motion. And I think soon enough, I can't see the counter here. Here, now I can see. Okay, let's move the movie a bit forward because I think you're getting the idea. So now it's moved so far that they're both out of here, but they will be falling back. I think this was the final escape. So finally, the yellow one, which was the middle mass, has escaped. Okay, so it took some 800 years in these units.
Excuse me, how do you know that it will never return?
So it's easy. You consider the escape velocity. If you have, once they're far away, it's to a good approximation, it's not a three-body problem, but a two-body problem, where you can replace the binary by a single guide. And then you know when two bodies are on a hyperbolic object or an elliptic orbit. If you like, you compute the total energy for this effective motion. If this total energy is positive, then it will be an escape. If this effective energy is negative, then it will eventually turn back and form some ellipse. Okay?
Barak?
Yes.
How about the fact that I think you convinced us once that it would be the smallest mass which would be ejected? Is that statistically more common or?
So you're getting ahead of us, but since you asked, it is indeed true that the lighter object has a higher probability of escaping. But all of them can escape. It's a random process. In this case, the middle one escaped. Also, in this case, you see that the masses are not that different. And in the limit, when all masses are equal, you'd expect that they would have equal probability. And this is indeed seen by numerical simulations. Okay, so in such a case, when the masses are not equal but nearly equal, you expect to see the lighter one escaping more often, but still with sizable probabilities for the other masses as well.
Okay, thanks.
Okay, so let us continue. This time I'm better trained, maybe, at changing back. Something wrong. Oh, here we go. Okay. And now, okay, I hope that you see back the PDF.
Yes.
Great. So now I want to go through a brief history of the three-body problem, again, because it has a lot of fascinating physics in it and also fascinating history. So Newton was the first, maybe the first to do physics, but at least is the first that we remember to do the three-body problem, since he was interested in the motion of the moon. And the motion of the moon, as long as we don't take into account just the motion around the Earth, but additional precessions that the moon displays, can be considered to be a three-body problem because these additional effects originate from the influence of the sun. So we have the sun, the Earth, and the moon. That's a three-body problem. And Newton devotes to it numerous pages of his Principia Mathematica. So that was 1687. Then several decades later, the problem of the moon continues to be interesting. D'Alembert and Clairaut in France compete over it, and they actually coined the phrase the three-body problem. And in fact, it was not easy to explain the motion of the moon because recall that originally people thought that the moon was moving on some kind of track. And then Newton says, no, it just hangs in space and held by the Earth, but then the sun disturbs it or perturbs it, maybe Jupiter perturbs it. So you might worry, is it stable? Is it going to stay? Is it going to go somewhere else? And in fact, these people at first thought that they would need to change the Newton's universal law of gravity in order to explain the motion of the moon. But later they found out that the motion of the moon can be explained just by the 1 over r squared law. Euler, famous Euler in 1767, found the first exact solution. This exact solution is periodic and collinear. Collinear meaning that the three masses are on the same line and they move in a plane while remaining collinear. Interestingly, these solutions hold for any values of the masses. So we usually know them in the extreme mass ratio limit or in the probe limit when one of them is much lighter than the other, but these solutions continue to hold in general. And also in general, they behave as if each of the masses is attracted by the center of mass. So each one of them moves on a conic section. It could be a circle, but it could be also some other conic section relative to the center of mass. And if the initial conditions are fine-tuned, they will move exactly in such a way that they move just with respect to the center of mass, to a force center at the center of mass, and they will remain collinear. That's one class of exact periodic solutions. And a few years later, Lagrange discovered another class of exact periodic solutions. These are the famous equilateral triangles, which again, they require very special initial conditions, and they have the same similar properties to those of Euler's. They're not collinear, but all the motion is confined to a plane, and each one of them behaves as if it sees only a center of mass with some mass, which is the total mass of the system. There were important advances in perturbation theory for this problem, but we will not discuss them in this talk. By perturbation theory, I mean if there is a large hierarchy of masses or if there is a hierarchy of orbit sizes. That's very important for the solar system, for the moon, and the Poisson bracket was invented for this reason, for this application by Lagrange and Poisson. Later, Jacobi found an special invariant or conserved quantity for this system, and that's the same Jacobi that invented the Hamilton-Jacobi method and the additional conserved charges. And there's a known important subclass of this problem, which is the probe approximation, namely when the third body is much lighter. So we call it the restricted three-body problem. And we consider the two others to be moving on a circle. So that's a circular restricted three-body problem. But again, our main concern is going to be comparable masses, what you can call generic masses. And we'll try to solve that problem, where you cannot use analytic methods. You cannot use perturbation theory. So what can you use? So people were trying to solve this problem to find an exact solution following the vision of clockwork universe of Laplace, or following the vision of determinism. We know the forces, we know the initial conditions, we should find the solution. But there comes Poincaré towards the end of the 19th century, and here everything changes. Poincaré was working on qualitative methods to solve differential equations. And then King Oscar II of Norway and Sweden, or Sweden and Norway, sitting in Stockholm, announced a prize in mathematics. He was advised by the mathematician Mitagle Flair, and Poincaré decides to submit an essay or a composition to this mathematics contest. And one of the possible subjects was the n-body problem, or the three-body problem. This was advised by a committee member, Karl Weierstrass, by the way. And he uses his knowledge and his recent new developments of dynamics to attack and engage this problem. And he discovers two very important, several very important, but I'll mention some of them. The first one is that this problem exhibits extreme sensitivity to initial conditions. This is what we call today chaos, okay? So Poincaré discovers chaos in the three-body system. He discovers Poincaré sections, he discovers Poincaré recurrences. He invents topology as we know it today out of this problem. He called it analysis situs, but later it became to be known as topology or algebraic topology. But to us, the most important consequence of Poincaré's work is first, the non-existence of additional conserved quantities, and secondly, that he believes that there is no analytic solution. So let me go back a bit to the order I wrote it. So first, he won the prize, even though he couldn't solve the problem, and he couldn't solve it even in an infinite series form. But he explained that the system exhibits this new kind of dynamical phenomenon, chaos, and this very strong mixing of all the orbits in phase space, which don't allow the existence of additional conserved quantities and don't allow to write an analytic solution. This led to him writing several volumes on a topic called New Methods in Celestial Mechanics. It took him about a decade, okay? It was one of his major works. It followed his initial interest and participation in this contest or prize. So he believed, and we believe, that there is no analytic solution. I should mention that the Finnish mathematician around 1910 named Sundman did write down a infinite series solution. However, it is considered to be at least completely useless, because even to follow a solution in circular motion for about 1 radian, it requires, according to one estimate, 10 to the 800 terms, okay? Very large number of terms, 10 to the 800. So this series, till this day, didn't find any use. It presumably converges, but this is an interesting question, but at least till this day, it didn't find an application. So there is a paradigm change here. We're no more looking for a clockwork universe, and if you like, we lost determinism. We know the initial conditions, and we know all the forces, but we don't know the future. Why don't we know the future? Because we never know the initial conditions to absolute accuracy. There is always some finite accuracy, some finite error. And due to this strong sensitivity on initial conditions, even if we know something for some first period of time, if we can predict the future to some typical time scale, we will not be able to predict it beyond this time scale. If you recall the movie, we can maybe predict the motion of the system up until the first close encounter, or maybe even the second. But if we want to go ahead to several close encounters, it becomes, for all purposes, it becomes a random process. It's like rolling a die. It's a similar question. It's just classical mechanics, but you cannot predict where the die, on which side of its sixth side, the die will fall, okay? Same thing here in the three-body problem. Here it was found first. So from that point, it was believed that the three-body problem is unsolvable. So if it is unsolvable, then we don't have to be interested in it, and we can worry about other problems. Or we should change the question that we are asking, okay? So maybe it is unsolvable, or maybe we were not asking the correct question. Maybe we should not be looking for an exact solution, since it doesn't exist anyway. Maybe we should look for something else. And here comes the progress of the 20th century. So computers come along, and two Russian researchers, Agekian and Anosova, were the first in '67 to perform computerized simulations of the three-body problem. So now you can follow the system. It is not always clear how reliable these simulations are, but they are believed to be reliable in probability. And I should mention another person that started very early on in the early 70s, Valtonen. He has been working on it for many years ever since, and in recent decades, he wrote two important books. One of them is called The Three-Body Problem, and it's a summary for physicists. And the other one, just 4 or 5 years old, is called The Three-Body Problem, From Pythagoras to Hawking. And that's a very good summary for the general public, believe it or not, okay? So what do we know from all of these computerized simulations? We find that if the total energy of the three-body problem in the center of mass frame is negative, then it will generically disintegrate into a binary and the third body. Why will it disintegrate? Well, first we should ask ourselves, can it disintegrate into three separate bodies? But three separate bodies, which are far away from each other, obviously have positive total energy, because the kinetic energy is positive, the potential energy is negative but negligible when they're far away. So if we constrain ourselves to negative total energies, then it cannot decay into three separate bodies. It can only decay into a binary plus one, and the binary will have negative total energy, so it works. And there is nothing that prevents it from decaying. So generically, it will disintegrate or decay. In fact, there are some stable motions which are stable and long-term and infinite-term without decay, but these probably require some mass hierarchy. So from simulations, what we see is that as long as the masses are comparable, it always decays. So maybe even with 100% chance. So this is similar to the principle that we know from quantum mechanics. Anything allowed will happen. Here it happens not because of quantum mechanics, but because of chaos. The system explores all of phase space, and since it is not forbidden by any conserved charges, at some point it will disintegrate. And now we can ask ourselves a natural question. Can we predict the outcome of this disintegration? We saw that it looks like a random process. It looks hopeless to predict it deterministically, to predict it analytically. But perhaps we can predict it statistically. Perhaps we can predict which one of the three bodies will escape. Perhaps we can statistically predict in which direction it will escape. Perhaps we can predict statistically the parameters, such as the energy of the binary, the energy of the third body, the angular momentum of each, the directions, and so on. Okay? So this idea was introduced already almost 50 years ago by a researcher, Monahan. He's from Monash University in Australia. And we have here just 9 degrees of freedom. We don't have here an Avogadro number of degrees of freedom. So this is not the usual statistical physics of thermodynamics that we may learn, say, from the approach of Landau and Lifshitz. This is the statistical mechanics approach, which discusses a small number of degrees of freedom, but looking at all of the phase space of the problem, as advocated for instance, as early as Gibbs. This was, in fact, the title of his book published around 1901 or 02, Statistical Mechanics, okay? So we have mechanics, and we're going to try and predict the outcome of these mechanics, although Gibbs did not discuss this specific system. And Monahan takes as his starting point the usual relation or equating probability. Yes?
לא רואים את השקפים שלך לא עוברים, אנחנו שתקועים על שקף מספר 11.
Thank you. Thank you very much. שקף מספר 11. So let's see.
The idea was to check the attention of the audience.
Is it moving now?
Yes.
Yes. Okay, so I should be changing slides in a different way. Okay, here, can you see the ones with the title Statistical Theory?
Yes.
Okay, good. So the audience is alert, as Tzvi says, and we can continue. So the basic assumption of a statistical theory is that probability is proportional to phase space volume, right? We have Liouville's theorem telling us that phase space volume is conserved, and we're going to equate probability with phase space volume. This is very standard. However, we'll see that this will be the difference in this work relative to previous works. So we'll get to it in a moment. Okay, now the slide changed. Great. So next I will skip many other works to a recent work by our colleague and friend, Nick Stone, and his collaborator, Lee, just from a few months ago. And they were able to evaluate the phase space volume sigma in closed form. This was not possible before them. Some studies did not consider all the conservation laws, for instance, did not consider conservation of angular momentum to make things easier. And the integrals, you have to integrate over a 12-dimensional phase space. So it's not easy to perform these integrations. So they were able to get a result to compute these volumes and thereby provide a distribution of outcomes or a statistical distribution of outcomes. It should be stressed that like all previous studies, they used this variable R, which is called the strong interaction radius. It's a kind of a spurious parameter. They call it a fudge factor, and they say it is unattractive. And the reason is they use it to cut off the integration because it is an unbound system. So if you want to compute, we hear one of you close your mute if you want to speak outside. Great, thank you. So if you want, you need it to introduce this strong interaction radius because the cutoff, the integration region must be cut off. And also, we'll mention it later, this phase space is divided into both regular motion parts and ergodic parts. And you need to introduce this cutoff in order to throw out most or some of these regular phase space which we're not interested in. Okay? So it's not a physical quantity, but it is introduced by all these methods into the theory, and we will see how it can be avoided. This will be one of the purposes of this work. Okay, so here we finished reviewing the history of the problem. We changed paradigm from seeking an exact analytic solution to seeking a statistical solution, but we understand now that the statistical solution is not available yet, and I will not show you a statistical solution either, but I will show you what I believe to be a significant step or a reduction on the road to a statistical solution. But why is this three-body problem important at all? Well, we saw that much good physics came out of it. It was important to understand the moon, but it's more than that. As we saw, it was the first chaotic system, and it became a prototype for chaotic systems. So as such, it is important also for other chaotic systems who may share some of the properties. Secondly, it has numerous astrophysical applications. For this, I will refer you to a good review of them in the paper by Stone and Lee. I will just mention that the tight binaries, which generate gravitational waves and are being discovered in these days, we don't know their origin, and there are several theories for the mechanism for originating these tight binaries, and one of them is three-body interactions. Another one is to understand the astrophysics of star clusters, where you have many stars relatively close, and then they form binaries, they form many triples. So we know that binaries are rather common in the universe, and we also believe that triple stars are rather common, but since they're unstable, they form and they disintegrate. So 2 reasons for importance. How did I get interested in this problem? I got inspired and interested by the work of Nick. I heard about it when it was on the news last December. And then it reminded me of that I was already interested in the three-body problem while teaching the course Analytical Mechanics 4 or 5 years ago. So I known already something about it and had already appreciated it. And seeing this beautiful progress, I got excited and couldn't stop thinking about it. And then I realized that there is something to improve, namely if one could avoid this strong interaction radius, this kind of cutoff. So I set out to try and eliminate that. I also had experience with a double pendulum, again, because I was curious about the course Analytical Mechanics, about this very simple problem, the double pendulum, a pendulum hanging from another pendulum. It's a system which has only 2 degrees of freedom, but nevertheless is chaotic. And I realized at the time that although it doesn't have an exact analytic solution, you can compute quantities statistically. And in fact, I did it. So I had some experience with that. So I set out to try and understand the statistical solution for the generic or comparable mass, non-hierarchical, so comparable masses, comparable orbit sizes, three-body problem. So before we continue to the results, are there any questions about the system or what we're trying to achieve? Okay, so maybe we'll keep questions to the end and I will proceed. The main point of this work is that we're going to change the value that we use to compute probabilities or probability distribution. Instead of equating probability with a phase volume or phase space volume, we're going to equate a related quantity, not the probability, but the decay rate or the distribution of decay rates, because it's really a decay rate. We have here decays, disintegrations, and we're going to equate it not with the phase volume, but with the phase volume flux. Okay? And the reason for this is that we'll take into account that the system is not closed system that runs in some finite volume, but it's an open system that finally decays. So rather than considering a particle in the box which is a good analog to a closed system, will consider a particle in a box, or have an analogy with a particle in a box. I'll show you a picture soon, but the box has a hole. And at some point, the particle exits the box. And while inside the box, it moves chaotically, ergodically, outside of the box, it moves in a straight line. It moves in a very regular fashion. So the important thing is the rate of flux, how much phase volume is exiting from the hole of the container outside. And this will give us both a different conceptual basis for the theory, and it will also give us different quantitative predictions, and I will show you some confirmation against simulation. So it will give us an exact reduction of the problem, we'll see exactly to what, and it will give us an improved fit to simulation. So this is really the main point of the talk, and now I'll try to tell you just what is this main result without going almost at all into the ideas and the derivation, just a very little out of this. Okay, so we're going to start now with formulas and with being quantitative. So the system can be described by a Hamiltonian. We have three bodies, we have the three locations and the three momenta, and the Hamiltonian is simply the sum of all three kinetic energies plus the potential energy, which is negative, and includes the three pairs that can be formed. The conserved quantities are the total energy, the total angular momentum, and the total linear momentum. And as usual, we can work in the center of mass frame, so then we can avoid the total momentum, and we're left instead with 9 degrees of freedom. We're left with 6 degrees of freedom after eliminating the center of mass. So we have 6 degrees of freedom, or 12-dimensional phase space, and we have 4 conserved quantities. So still we have quite a number of degrees of freedom, 6, and quite a large phase space. So we know the initial conditions, so we know the initial conserved quantities, they remain conserved, but other than that, the point describing the system fills out practically much of the volume that it can fill in phase space, subject to the constraint of energy and angular momentum. So the next step that we're going to do is to separate phase space into several regions, because we saw that the system, if you recall the simulation, really has very distinct kind of motions. Oh, but before that, sorry, okay, I was trying to remember the order of the slides. Before that, I want to describe the outcome parameters, okay? So we said that eventually our three-body system will decay into a binary and a free body, going away from each other, okay? So by the binary system, I mean these two. So if I ignore the third guy, I can associate a binary energy and angular momentum of the binary and some phase for the perihelion, or sometimes called the longitude for the perihelion or pericenter, maybe is more appropriate, pericenter. So we have some conserved quantities for the ordinary Keplerian motion of the binary, and once they have decayed, the third guy doesn't affect it very much, so it's really described by Keplerian motion. On the other hand, the relative motion of the binary and the third guy can be represented by a hierarchical effective system gotten by replacing the two masses by their total mass and putting it at the binary hop. Do we see still the slide outcome parameters? Yeah, okay. So we replace the mass of the binary at the binary center of mass, and we get what I call the hierarchical effective system. Okay? And this hierarchical effective system is to a larger amount decoupled after disintegration from the binary system. So we really have two decoupled systems after decay, the binary system and the hierarchical effective system, each one of them is moving on a Keplerian orbit. This one is moving on a open, scattering, hyperbolic Keplerian orbit, and this one is moving on a bound Keplerian orbit. Each one of them has energy, angular momentum, and Laplace-Runge length vector, or if you like, a phase or longitude for the pericenter of the motion. Okay, so these are the variables, and this is the decoupled limit after everything has happened. These conserved quantities are related to the total conserved quantities by the conservation laws. So we see them here in the diagram. For instance, E is the total energy. So obviously it will be equal to E of the binary. If it doesn't have an index by convention, it's the binary. So it's the energy of the binary plus the energy of the effective system. So their sum is obviously the total energy. Similarly for the angular momentum, only here we have vectors. So this is L, the total angular momentum of the whole three-body system. And after decay, we have L orange, which is the angular momentum of the binary. And we have L effective, which is the angular momentum of this hierarchical system. It's related to the impact parameter, if you like. And the sum of these two vectors must equal the total angular momentum. If we look at the plane where we draw both the size of the binary angular momentum and the binary energy, then they fill this space. Oops, sorry. They fill this space, and for fixed energy, the angular momentum can have any value up to some maximal value. Why is it moving? This maximal value here, over here, corresponds to circular motion. So this line corresponds to the equation E times L squared equals a constant, okay? It is, this inequality is saturated when we have a circular motion for the binary, and otherwise, if we have an elliptical motion, then it is an inequality. And this constant, which will play an important role later, I call it the binary constant, is equal to the reduced mass mu of the binary times this gravitation, the constant of the gravitational potential squared. Since we can form three different binaries out of three bodies, we can form three different binaries, we will have three different K constants. Okay, somehow there's something chaotic about the mouse or something, and it's running to other transparencies, so I have to try and control it. Okay, so these are the values, the description of the system after decay has occurred, and the different parameters that we can use to describe the decay. And then our objective would be to have a statistical theory. So to say, given some element of values of the binary energy, the binary angular momentum, and the effective energy, the effective angular momentum, and so on, what is the probability to find the particle, the system there? In fact, we'll ask, how much time will it take for it to decay also? So what is the decay rate? Okay. And now the next step that we're going to do, and that's already a new point, we're going to imagine or to visualize the phase space as being made out of several regions, okay? This is not a picture of the phase space itself. The phase space itself, as discussed, is 12 dimension, and at this time I don't have a useful true to life picture of it, but I have a schematic picture of it, schematic diagram by this piping diagram. And on the left side, we see the kind of motions which are hierarchical. So it either describes an escape which will not return, or it describes what we call a sub-escape excursion. A sub-escape excursion are these cases where one of the three bodies is ejected, but then its velocity is below the escape velocity, and then finally it falls back in. So this pipe here is actually closed, and at some point, the system, which is described by a ball or by a small point moving in this phase space, will some point hit a wall and return back. While here, if it goes to escape, it runs to asymptotic, it runs to infinity. Okay, so this left-hand side describes the hierarchical motion. The right-hand side describes the genuinely three-body motions, and that also falls into two parts. We can have regular motion, such as flyby. The third guy is flying by and just exiting. Okay, here is the binary, and it can just fly by and get out. Or you can have an exchange when this binary is rotating. The third guy is really getting close to one of them, kicking it out and replacing it. Okay, so this is called an exchange interaction. This can happen in a regular way, in a way which is not extremely sensitive on initial conditions, not chaotic. So I use regular to distinguish it from chaotic. And so there are several possibilities for regular motion. Regular motion is relatively short, but we can also have ergodic motion. So the system described by a point can fall into this ergodic container, and then it can hit the wall many times, move in here for a very long time, but eventually it will exit this hole. Okay, so this is this mental picture that I already mentioned of a leaky container. We think of phase space as having an ergodic region, but this ergodic region has some exit holes, and we're going to consider the flux of phase space volume outside of this hole. We're going to evaluate it and use that as a measure of the quantity of interest, namely the decay rate or the distribution of decay rate. Okay? In fact, we can even write an equation for the statistical evolution of the system. So for instance, we may assume that we start with initial conditions where the system is in the ergodic region with probability PE equals to 1. And then we may ask, how will the probability now evolve with time? With time, it can go either to the escape with some probability or to the sub-escape, and then it can return from the sub-escape either back to the ergodic region or to the regular and back. So there is here, you can write a system of equations. We've written a system of equations which describes it. I will not go into it now in detail unless I'm asked about it, but we have here three variables: the probability of being in the ergodic region, the flux of coming from the left, from hierarchical motion, and the flux for coming from the right, from the non-hierarchical motion. And there are several parameters that appear in here, the most important of which is the decay rate, which tells us what's the rate to decay from the ergodic region outside. Or alternatively, what's the decay rate from the ergodic region to go either to a sub-escape or to an escape. This is where we're going to have some closed form expressions. Okay, so far it's an equation. This equation, by the way, as its solution has very interesting properties. It describes an exponential distribution of decay times for some period of time, and then it changes into a power law distribution. So it gives us a transition from an exponential distribution of decay times into a power law distribution of decay times. The exponential one comes from this kind of radioactive decay, familiar radioactive decay over here. And the power law comes from the very long sub-escapes, which are distributed according to a power law for a reason that takes a few lines to explain. Okay, so this is decomposing the phase space into several components. And here is the main result. The main result is an expression for the decay rate as a function of U. U are these outcome parameters, the binary energy, the effective energy, the binary angular momentum, the effective angular momentum, and so on. And this expression is given as an exact product of two functions. One of the functions describes the flux of phase space, which we evaluated in closed form, and I will explain all the notation. And the other function is called emissivity or absorptivity, and we know very little about it. We know only that it is bounded. Okay, so this is the main result, the exact reduction of the decay rate to the distribution of decay rates into a product of two quantities. One of them is now known in closed form, so that's the progress. And one of them still requires study, but is hopefully easier to understand. And all of this is defined by the total phase volume, which needs to be regularized. So this is called the regularized chaotic phase volume. Since it's just a normalization, I will not spend time on it right now. So let me just try and explain the notation inside this main result.
Barak, just a moment, please.
Yes.
In what sense is this result exact?
Good. So it's an exact result under some assumptions of the model, mostly the ergodic assumption. Namely, we're assuming that any given particle is moving the same as a whole ensemble of particles. And in fact, as I will show later, computer simulations show that this assumption holds to a very good accuracy, okay? So I'm assuming the ergodic assumption that we can replace time averages by ensemble averages, or that the motion in phase space is completely random.
Barak, but you know that, mathematically speaking, this is an uncontrolled assumption. I wouldn't call a result based on an uncontrolled assumption exact, but maybe it is a matter of taste.
No, you're absolutely right, Baruch. It is an uncontrolled assumption. It is an exact result within this assumption, okay? Let's be very precise. Within the assumption of the ergodic approximation, this result is precise, is exact. Okay? Okay, so now, what is the notation here? So D gamma is the differential decay rate. How much probability per unit time is going out into some unit of binary energy, some volume of angular momentum, and so on, okay? That's the amount of probability per unit time. Emissivity, this calligraphic E, I will discuss a bit later. It's a number between 0 and 1, which could depend on the parameters U. Now here we have this quantity, which actually describes simply the period of the Keplerian motion, of the binary motion. So we have here the same constant Ks, which I mentioned before, this binary constant. And this expression is simply the period of that binary motion. And then we have D3L, D3LF, but subject to conservation of angular momentum, divided by the size of the binary L and the size of the effective L. This very simple form is a direct consequence, it turns out, of the fact that we're discussing central force motion. Both the binary motion is central force and the effective motion is central force. So this gives this simple expression over here. And then the flux is equally distributed over the pericenter phases. Okay, so I think I explained the notation of this closed form expression for the flux. It describes the flux of the outgoing phase volume. And this is a very well-defined quantity, and it can be computed exactly. The problem is that not all the flux coming out of the ergodic region reaches infinity. And this is taken care by defining this emissivity. So this emissivity is kind of the fraction of all trajectories. I here do some averaging over the binary phase, a phase going from 0 to 2 pi divided by 2 pi, and mu here is the measure. So it's the weight of all trajectories coming out divided by the total number of trajectories, if you like. And we have this general equivalence of emissivity equals to absorptivity. This is known as Kirchhoff's law of radiation. Okay? So I will say a few words about it in a moment. Okay? So again, within the ergodic approximation, we have this reduction that we know the flux in closed form, and it remains to study the emissivity or absorptivity. They're the same. This has to do with the fraction of orbits with given parameters where I send the particle from infinity. Will it fall into ergodic motion, or will there be just a regular motion, flyby, exchange, something, and will go out? Okay? Before I discuss this problem and mention some of the derivation, is there any question? I will go over time by some 7 minutes. I apologize.
One small question. Sorry if I missed this, but what's the bar over the phase volume mean?
That means that this phase space is regularized. So the phase space is infinite, but we here consider a regularized chaotic phase volume. This quantity was not studied in depth yet, but the article contains a definition of it. Okay? So this will set the scale for the decay time of the system. So far, people studied only the distribution of decay outcomes. And obviously, if you have a higher decay rate to some channel, then you will also have a higher probability. But what is the total time that it takes to decay? That's the first paper, I believe, that suggests a theory for this. And for that normalization, it's important to know also the regularized chaotic total volume. It's kind of the total volume of the box. Only the problem is that this box is infinite. So we need to define it in some regularized way, this volume, because the three-body problem is unbounded. Okay? Thank you.
Barak?
Yes.
I have a question. You defined the sub-escape regime.
Yes.
How is it technically defined given that the system is still mathematically bound? The total energy or the energy of the escapee is still negative with respect to the binary. So how is it technically different than the ergodic
Good question. Good question. So how do we distinguish the different regimes here? So if two of the bodies are much closer to each other than the third guy, okay, we have a large separation, which is larger than the typical separation. Then we're on the left-hand side, either in the sub-escape or in the escape. Okay? If the distances are comparable, or they are not comparable, but just for a short time, because for a close encounter, so it's an issue of typical times and typical distances, so we can be on the right-hand side. So on the right here, we have alternations of close encounters and comparable distances, which are all within the typical distance. This is in the ergodic. In the regular, we have something similar, but much shorter. In the sub-escape, we have very far away and for a long time, not alternating close encounters, but for a long time and very far, and this kind of configuration. And an escape is for infinite time, something like this. Okay, so each one of these regions is defined rather well, but of course there are also some gray zones in between them, at least between some of them. Okay, so now I want to show you what was done by a team of simulations. This is the team of Manwadkar, Lee, and Trani. It's already published on the archive. I don't have here the archive number, but you can find it. And the setup for their simulation is a closed binary moving in a circle, and the third guy quite distant away from it, some 20 times more distant than the diameter of this motion, initially at rest. And then they leave it. And sometimes you have ergodic motion, sometimes you have regular motion, like an exchange, and you can measure various outcome probabilities. And in particular, you can measure the escape probabilities. So for now, I will concentrate on the escape probabilities. And let's look at the results and compare it to several theoretical predictions. Let's start with the easy case of the equal mass. You see here 15, 15, 15, right? So one of the 15 is the infalling one, and the other 15 were originally inside the binary. You see that the measured escape probabilities are, to a very good approximation, equal. So this relates to Baruch's question before. We see that at the per mil level, the system is really ergodic. It forgets about its history. It forgets that 15.0 was the one who actually fell in, and 15.1 and 15.2 were the ones who were originally inside the binary. And at the per mil level, they have equal escape probabilities. Of course, all theories predict also equal probabilities because the theories don't know anything about initial conditions. They just consider the three masses. Now let's consider the three different theories that I'm comparing here. I'm comparing the prediction of the current paper, but ignoring the emissivity. If you like, I'm setting the emissivity to 1. The logic being that since this ergodic, this escape probability considers all possible events, populating all of the outcome parameters space, we kind of average over all the emissivities, and therefore, because we average over all of the emissivities, we consider the emissivity to be constant, okay? So that's logic, it cannot be proved, but the nice agreement tells us that something is right about it. So this is this prediction. The second prediction is the prediction of Stone and Lee from this year. And the third prediction is from the book by Valtonen and Kartunen from 2005, where they state that the probabilities are inversely proportional to the escape mass, simply to the escape mass, okay? I should say that the theory presented here is proportional to this binary constant to power 3/2. Maybe I will say one sentence why. That's because for a given energy, this angular momentum, we call it L0, the maximal angular momentum for maximal binary energy. So this quantity is L0, and from this inequality, you can see that L0 is proportional to square root of Ks. And for this scenario, for this setup, the escape probability is proportional to this L0 cube. So it's proportional to Ks to 3/2. And I didn't repeat here the definition of Ks. Here it is, oops. It satisfies the condition that that it is largest for the lighter escape mass. So the lighter the mass, the higher the escape probability. So this is satisfied by this. It is satisfied actually by all three predictions. Here also you see it manifestly satisfied. The lighter the mass, the larger the probability. But now when you compare the numbers of these three predictions with the measurements, you see that this prediction is, you may even call it surprisingly close, since we did assume the ergodic assumption and we did take the emissivity to kind of factor out, you can see that the numbers are in very good agreement at the level of 1 absolute %, I would say, yes, in all these two other cases of unequal masses. Whereas the two other predictions, they also give you a higher probability for the lighter mass, but you will see that some method gives an overshoot of the inequality of probabilities. The other method gives an undershoot of the inequality of the probabilities. Really, it appears to be really a significant difference here, and we're still in the process of further studying and comparing these ideas with simulations. In principle, you can do an exact test by measuring epsilon, the emissivity here, or calligraphic E, from its definition in a scattering experiment, and measuring d gamma from a decay experiment, and you could really compare and see whether this equals that. So that, as again, Baruch mentioned, it depends on the theory, and it depends on the ergodic assumption, which appears to be satisfied in this case to a good approximation, okay? So this is a good evidence for agreement. Since we don't have time, I will skip the main ideas in the derivation. I mentioned them, I think I mentioned most of them already, and I will just end with a discussion. So unlike all previous systems, all previous studies, of the statistical approach to the three-body problem, this one is flux-based, and this one studies decay times, not only the outcome distribution, but also the time of decay. It provides an exact reduction in the sense that we discussed. It does not include spurious parameter, the strong interaction radius, so if everything was regularized appropriately, and it gave us, at least in the case that I showed you, the escape probabilities, and improved the agreement with numerical simulation, okay? In this sense, I consider this problem to be cracked, not to be solved, but to be cracked. So now it reduces to considering the study of the emissivity or absorptivity, it's the same, and to consider maybe later corrections to the ergodic approximation. However, it appears that the ergodic approximation holds very well in this system. Namely, it's very random, very ergodic. So we will start with studying this function, the emissivity or absorptivity. How does it depend on the outcome parameters? And in this sense, I think we now have a solid foundation for the statistical theory envisioned almost 50 years ago. And I thank you very much for your attention under these Zoom conditions. And if you have any questions, of course, I will be delighted to answer. Thank you.
Barak.
Yes.
How long on the average are we going to have a moon?
This is Shmuel. Hi, Shmuel. So when the masses are comparable, it appears, there's no theorem, but it appears that the chance of decay is 100%. However, the moon is not comparable mass to the Earth and the sun, of course. And in fact, for such systems, we have, I believe, a theorem that it is stable. So I believe the moon is stable. And we also know that the so-called Lagrange points 4 and 5, the ones of the equilateral triangle, they are also stable in the extreme mass ratio limit. So there are some regions of phase space where the motion is regular, and even though it is not protected by a conserved kind of global conserved charges, it is still protected by something else. And for these cases, the perturbative cases, the extreme mass ratios, the system will not decay, but for comparable masses, it does decay. Did I answer the question?
Thank you.
But Shmuel, the moon is receding from us. It used to be much closer in the past.
Yes, it is evolving a bit, right? Because of the tides.
It's receding, but eventually it will get back.
Mm-hmm.
But I think as far as I remember, Avishai, as far as free body is concerned, it will not escape.
I agree.
I think it is limited to a Hill sphere around the Earth.
Mm-hmm.
So that's another very known researcher in the three-body problem,
It will not
Hill,
escape,
but we didn't have a chance to discuss it today. Yes?
There's not enough angular momentum in the spin of the Earth to eject the moon.
Mm-hmm.
Well, and of course we didn't incorporate spin at all so far.
Yes, but
that's
for
another
the
interesting
dynamics that pushes the moon away, this is necessary.
Thank you, Rehem.
Barak, I have a question which is sort of not exactly what you solved, but it is related. You mentioned some astrophysical motivations. So a very relevant astrophysical motivation is a three-body problem for the case in which there is a binary and a third star is coming in and interacting.
I stopped hearing you. Can you repeat, Zvi?
Well, my internet it tells me that my internet connection is unstable, so I apologize on behalf of Kaveh Zahav for the quality of their service. Now, the point is that a very interesting astronomical problem that that is related to what you study is when you have a binary and then you have a third star that comes, interact with them for a little while, and then it escapes. So in this system, typically the total energy is positive, and the outcome is usually that something else is kicked out. And in the 80s, I think Pete Hart worked a whole library of numerical solutions of what can happen for these cases. So my question is whether the method that you suggest here can shed some new light. He did not manage to find the sort of analytical summary of what is going. He just had this huge set of tables, which is the guidance. But is there any analytical guidance from what you have done here that can be used for this kind of very different three-body problems?
Right. So we can imagine two kinds of initial conditions for a three-body problem. Either they're already in a three-body configuration, they're close by, and then it's a question of decay, it's a decay experiment, or we can imagine some kind of scattering experiment. We have a binary, we have a third guy shooting at it, and that's the question that you're asking, a scattering experiment.
Yeah,
and then
exactly.
we want to know what is the distribution over possible outcomes, which was the subject of this talk. And then there are really two separate questions. The total energy can be either positive or negative. Because since the binary has negative energy, it could be that the total energy is still negative. And then this is exactly the subject of this talk. Okay? So it depends how large is the kinetic energy of the third guy, if it's enough to overcome the negative energy of the binary. If it is large enough, then the total energy is positive, and all these techniques will not apply. The theory would be very different. I don't know much about it. Maybe Nick or somebody else knows about it, but the system will be much less stable because this negative energy kind of makes the holes in the ergodic region small. And if it is positive, then it can decay now to three bodies, and it will either decay three bodies or it will have a flyby or an exchange, but it is likely to just explode the whole thing into three objects if the total energy is positive, okay? So I know very little about it. I expect it to be much less stable, decay much faster, much less statistically. You see, one of the points of the system that we studied, the negative energies, is that it is so chaotic, so ergodic, that while you cannot have any analytic solution, you have a good chance of having a statistical solution. For the positive total energy, I don't know if you can have any analytic solution, but I don't expect much of a statistical solution either, because it is short-lived and it will not have time to ergodicize or thermalize. So it will really be solved by a numerical simulation, given some initial conditions, but there is very little that you can say for a specific initial conditions. You might be able to say something about the whole family of initial conditions, about the whole family of trajectories in phase space. So if someone has anything to add to that, I'd be interested, but that's my very little knowledge that I can relate to.
Yeah, I can comment on that if you guys are curious. I think it's basically as Barak says, in the limit of very high positive energy, everything decays very quickly and the motion is not particularly ergodic. And in fact, Pete Hutt, the astronomer Tzvi mentioned, did develop a way to think about that regime using the impulse approximation and a more deterministic approach. But there is a very complex regime where the energy is mildly positive and you have a finite probability of a 2+1 outcome and a finite probability of a 1+1+1 outcome. And there it's very unclear what to do other than use numerical simulations.
Good. So there is some analytic or perturbative regime, but there's also a very non-perturbative regime.
Yeah, if you think about the ultra high energy, positive energy limit, you can imagine a binary single scattering where the single star shoots through on much less than the orbital time of the binary. And then you can just treat it in an impulse approximation sort of way.
Right.
I guess I have one comment. First of all, the agreement with this discrete probability of different masses getting ejected is very impressive, and I think is a nice sign that you're onto something new and important here. My one comment is about this strong interaction region parametrization, which I agree it has something spurious in it, but I don't think the concept itself is spurious. What I think is spurious is the exact parametrization, which was fairly ad hoc, that Nathan and I used in our paper. But I think it is connected to a physically meaningful concept, which is sort of the barrier that you've defined also between the ergodic zone and what you call excursions, I think in your language. There is some sort of not a hard barrier, but a length scale delineating those two regimes. And I think that is a physically well-defined thing, even if it's hard to write down the parametrization in a closed form.
Yes, I completely agree to this comment. But at the same time, there is something quite arbitrary about the choice of this R. There is a certain ratio number, right, that appears in the theory, which is quite arbitrary and can be tuned. So there is something left to be hoped for. And I think you even say it in writing in the paper.
No disagreement about that. Our parametrization was fairly arbitrary, and we were lucky in a sense that our results did not depend too strongly on it. But I think the concept itself is a physically meaningful one. And if one could come up with a more exact parametrization of it, it would be interesting to compare that to the regularized approach that you have.
Okay. At any rate, I think that your result is beautiful. I think I should, it wouldn't hurt to stress it again. And one thing I didn't know, that we didn't know, there is the theory for the three-body problem. You know, it's a problem that was at the forefront of science at the end of the 19th century. And now it has been studied for many years since then, but I wasn't aware of the status. And then it turned out that you were able to get a closed form expression and to overcome several of the obstacles that were present there. And I thought it was very interesting and inspiring.
Oh, thank you. And I'm very happy to see you developing this further. And I guess just to finish my thought, one other thing I would be curious about is to see whether or not the regularization technique you've applied could apply to other kinds of self-gravitating dynamical problems, because this divergence of phase space is a generic feature, as you know, of statistical systems that are dominated by long-range forces, which are very prevalent in my own field of study. So it would be interesting to see just how many kinds of stellar dynamical problems could be, the phase volume infinities could be regularized away in.
Thank you. Thank you for the
Barak?
Yes.
This is Lazar. I have a question. In your
I can hear you but cannot see you.
Okay. In your theory, you somehow assume that the masses of the three bodies are comparable.
Right.
But this is not a well-defined word, okay? Comparable. So the question is when one can use your theory and when you cannot. For example, if one of the masses is 10% of the other two, will it work?
Good. So I think the answer is that comparable means it's an issue of radius of convergence, and obviously the radius of convergence is something like 1. So that means that as you get to something like 10%, as you reach about 10%, I would expect it to be less accurate, and I would expect the extreme S ratio techniques, the analytical techniques, to start being more applicable. And this requires also, this is also an issue of numerical study. So numerics, we hope to push them to higher unequal masses, higher mass inequality, and that would give us some information about how accurate the theory is in face of higher inaccuracy. But in generally, if you have a theory of a quantity that is good at 0, let's call 0 being equal masses, let's call completely unequal masses 1, then you expect it to be good up to an order of some radius of order 1.
Is my question somehow related to the relative size of the chaotic region in phase space?
Relative
because
size.
if one of the bodies is very small, then the problem is basically integrable or closely integrable, like the sun, moon, and the earth problem. So the chaotic part of this problem is probably, part of the phase space is probably very small.
First, even in this case, even in the probe approximation or the restricted three-body problem, it is non-integrable. Even a planar motion with just 2 degrees of freedom of the probe, even that is non-integrable, okay? There is some part of phase space which is well-behaved and regular, but the general motion of the restricted, even planar 2-body problem, this was exactly what Poincaré studied, and this is exactly where he discovered chaos, I believe. But this is a side comment. Your question was, just a minute, I got caught on correcting that, and I forgot your main question. Can you repeat that, please?
I was asking a question, what does it mean that the masses are comparable in your theory?
Well, no, but that we said.
And then somehow I felt that actually the problem of comparability of masses is related to the problem of how large the volume of chaotic motion in phase space.
The volume of chaotic motion.
Compared to the regular motion.
Well, I don't know. I cannot comment much about it. It is true that it becomes more amenable to analysis as the mass ratio becomes large. However, it still remains, at least part of phase space does remain chaotic, even in the extreme mass ratio limit. Okay? And I don't know how to quantify it at this time.
Okay, thank you.
Okay. Are there any further questions or? Okay, in that case, no? Okay. In that case, I thank everyone for the really lively discussion and on all the questions, and see you at some other opportunity.
Thank you, Barak. Thank you.
Thank you.
Thank you.
Yep. Thanks for the nice talk.
Thank you. Goodbye.
Thanks, Barak.
Okay, I have to end the meeting.